What's up, everyone? Obviously, you know who I am. Definitely, you know who I am. I don't have to introduce who I am. Um, so previously, we did a little bit of okay. If the question that I asked, if you don't know who I am, you know who I am. I don't mean in a way that the guy who teaches physics, but actually a guy who's obsessed with Valentina Gomez. I am the guy obsessed, like fucking obsessed with Valentina Gomez. And hopefully, I do end up as Valentina Gomez famous student because I don't look at Valentina Gomez as know, as a big fan, but I look at her as a teacher. Anyways, so previously we have done the continuous probability distribution and a discrete probability distribution, and we did speak about normalization. We did state that we are going to do normalization. So my my plan for this today itself, so 25th of April 2025, is that I plan on finishing the entirety of chapter 1 before moving on to chapter 2, because chapter 1 you shouldn't focus as much, but it is still important. Anyways, normalization. So first of all, what is our normalization condition? So, what is the condition that must be stated to ensure that it is normalized? Pretty simple. The sorry, the the range from minus infinite to plus infinite, psi of x and the whole square must equal 1. Psi, this is what you call a wave function, right? And it is only used in quantum mechanics because everything is probabilistic. You cannot say f of x and t. It's like f of x and t, but in the quantum point of view, not the classical point of view, right? So, oh, sorry, my bad. So psi of x and t whole square must equal 1. Now, why do I have square? I can finish the rest of it. So rho of x and t. So this means the probability distribution for x and t. Now, why do I have square? Anyone? The reason I have square is because psi is written in the form a plus iota b. Okay, if you can see that, is because my iPad has this updated version where it automatically solves anything, but it's not able to read the values properly. A plus iota b. So this is the equation that a wave function is represented in. This is the wave function it is represented in, right? And if I were to just, a probability must always be a real value. So core concept, core thing one must know is that probability must always be a real value. The probability must almost always be a real value, regardless of what you do, regardless of what you say, regardless of what anything comes up with. Probability must always be a real value. And the wave function having a complex conjugate in it makes it much more shittier. And the only way we can actually eradicate that is by doing the square of it. Now, iota is a value itself, which is minus square root of 1. But if I square it, I end up as minus 1, right? Real values remain real values, nothing changes to that. The complex values will change, and I am going to explain to that why does I square end up minus 1. I am going to explain that. Don't worry about it. But one thing to clarify is that psi of x and t whole square must equal 1, such that the wave function whole squared is the probability of the particle at that specified time, not depending on whether you're doing a time independent Schrodinger equation or a time dependent Schrodinger equation. So as long as your rho of x and t must equal 1, meaning the every continuous infinitesimal functions, infinitesimal steps that we try to integrate one by one by one by one by one, we try to integrate every single one of them and they must collide to 1. Cool? So that is your first normalization condition. Step 2, the time derivative. Remember, now this will be a very good reason why you need ordinary differential equations. So time derivative for normalization. So this will be the time derivative for normalization, and it is also important to know why you need ordinary differential equations. This here, d by dt of minus infinite plus infinite psi of x and t whole squared dx ends up as what? Curl by curl t psi of x and t whole squared dx. Now, in ordinary differential equations, we are going to explain something called partial derivatives. This happens when you have two or more functions inside the two or more variables inside a function. And inside the function, inside the variable, we have x and t, the position and time. And now you cannot do d by dt when you have two variables. D by dt only works for one. So if you have d by dt for two, you would have to differentiate for both of them, which is beyond impossible. And I mean, it is possible. I can do it. Definitely, I can differentiate both of them. But in the essence of saving up your time while making your calculations easier at first, I mean, obviously this is quantum mechanics, right? This is a quantum mechanics lecture. This is not some game. Second of all, it will be very difficult for you to solve both of them. I can. I can use d by dt and solve both of them, but nobody else can. Should not. It is not recommended. Easiest thing you can do is partial differential equation, because two variables exist, two independent variables exist. Why do you want to focus on both of them? And in a sense, if you want to differentiate one, leave the other, you'd have to partially eradicate one. You see that partially eradicating one variable? So when you partially eradicate one variable, typically you'd have to go through partial differential equations. Partial differential equations. And where do we learn them? ODEs. This is the core reason why you need ordinary differential equations. Now, this is how you would calculate the time derivative for the wave function. Cool? This is how you would calculate the time derivative for your wave function, partial differential equation. Now, the next step, the next step will explain why multivariate calculus is important. So this will explain why multivariable calculus, which is calculus 3, is important. Psi square is what? Psi times psi. But psi is what? Psi is a complex equation, right? Psi is a complex equation. Now, psi, obviously, psi square is psi times psi. And when you do the equation, which is a plus iota b, you'd have to do a plus iota b, a plus iota b conjugate. So conjugate means it swaps the operating sign for any value that has an imaginary value in it. So IB has an imaginary value, which is a plus IB. And if I take the conjugate of it, I would end up having a minus IB, indicating that I have changed Because this is a complex value, I would have to change the sign of my complex value. A is a real value, that doesn't change. I is not a real value, that changes, right? So eventually I'm going to have A plus IB, A minus IB. And where will you learn that? In Calculus 3. Will I teach here? Nope. So if I use number 2, which is curl by curl T of psi square, which is psi conjugate curl psi by curl T plus curl psi conjugate by curl T of psi. What did I do? Again, you also need what? You need an ordinary differential equation knowledge here. So I'm going to explain briefly what's going on. Curl by curl T of psi square. Now psi square is what? Psi square is equivalent to psi of x and t. We did that. It's right here. Psi square of x, psi square is the same thing as psi of x and t whole square, right? Pretty simple. And if you want to differentiate a wave function in respect to time, while having psi of whole square, if you want to partially differentiate the psi square, and we know this typically means curl by curl T of psi times psi, which means it is curl by curl T of psi of x and t times psi of x and t, right? Psi of x and t times psi of x and t. Give me a page. Just give me 2 seconds. So it is psi of x and t times psi of x and t. And psi of x and t is what? If I do the partial derivative for psi of x and t, this ends up as what? You know the product rule, right? Product rule is simple. So eventually you're going to end up with psi times curl psi by curl t plus curl psi by curl t psi. Psi of x and t, this is for this guy here. This is for this guy here. Right? Simple. Again, more lectures will be done in your ordinary differential equations. So be aware of that. Now this leads to one thing. We have explained in chapter 1 the Schrodinger equation. The Schrodinger equation. What do we know about the Schrodinger equation? It is iota h bar curl psi by curl t is equal to minus h bar square upon 2m curl square psi by curl x square plus v psi. Right? We did that. And now what you want to do is based on the equation. If I look at this equation again, this right here, oh, not that right there, and this right here, actually, the entire thing. If I look at this equation here, I have a what? I have a, oh shit, I have a curl psi by curl t, right? I do have a curl psi by curl t. What will I do now? I'm going to give you 5 seconds. I have a curl psi by curl t here. I have a curl psi by curl t here. Your perception could be right, but it is dangerous. Your perception can be right, but it's dangerous, right? If you said swap, like substitute, you're right, but don't do that directly. It is going to be very dangerous. It's not easy maths. It is quantum mechanics. So if I'm going to write the equation again, so iota h bar curl psi by curl t is equal to, so I have iota h bar curl psi by curl t is equal to 1442 is equal to minus h bar square upon 2m curl square psi by curl x square plus v psi. I'm going to divide this entire thing by iota h bar, right? And then what leads me to is minus iota h bar upon 2m curl square psi by curl x square plus minus, not plus, minus iota by h bar v psi. Why is it minus? One thing, I have a complex conjugate in the iota h bar. When I move from left to right, I am going not only, I'm obviously, if you move from left to right, your operation changes. If you have a multiplication, it ends up division, which is for everything. But for complex values, if I were to move from left to right, not only your the multiplication or division operation changes, but your addition or subtraction operation changes for real values. This is a complex value. This is an imaginary value. And if I move from left to right, my sign also changes. So this not so iota h bar, this will typically be minus iota divided by h bar v of psi. Cool? All right. And now we also have a complex conjugate. So curl psi by curl t conjugate, which is minus iota h bar by 2m curl square psi by curl x square plus iota by h bar v of psi. I made a mistake. This should be a positive, not a negative. Right? I made a mistake. That should be a positive. Cool. We did curl psi by curl t. Got our first equation, which is iota h bar by 2m curl square psi by curl x square minus iota by h bar v of psi. And we did curl psi conjugate by curl t, which is minus iota h bar by 2m curl square psi by curl x square plus iota by h bar v of psi. Now, what is psi whole square? Psi whole square, it is psi times psi conjugate. Remember psi times psi conjugate, or did I not mention that? Yeah, psi conjugate times psi. Oh, I thought, okay, maybe you might presume, maybe I said multiplication, but this is not multiplication. So it'll be psi conjugate psi. Psi conjugate psi conjugate psi. Psi conjugate multiplied by psi. Right? And obviously this is psi times psi conjugate. Psi, what was the psi equation? I mean, even though it's a good practice to write psi conjugate first, but I'm going to write psi, I mean, because I know what's going on. As long as I know what's going on, right? So I'm going to have iota h bar by 2m curl square psi by curl x square minus iota by h bar v of psi. And then I'm going to, actually, you know what? I'm going to move that there. So I'm going to snip this equation here. Oh my God. I'm going to snip this equation here, copy that, bring it here, and remove all that red section there. Copy the same thing. This time I'm going to add m minus, and I'm going to add a plus here. Right? Let's combine them. Let's see, I have iota h bar by 2m curl square psi by curl x square minus iota h bar minus iota by h bar minus iota h bar by 2m curl square psi by curl x square. So I'm going to multiply these two. I'm going to have iota h bar by 2m. I'm going to have iota h bar by 2m curl square psi by curl x square minus iota h bar by 2m curl square psi by curl x square plus iota h bar by 2m curl square psi by curl x square iota by h bar v of psi. And then I'm going to do the same thing. So typically this gets cancelled out because I have the plus for same thing. I'm going to have the minus for same thing. So this is going to get cancelled out. And I have a minus, that'll be a minus, right? Yeah. And then minus iota square by h bar square, actually minus, I'm going to do one thing, iota by h bar v of psi, iota by h bar v of psi. So that's just the square of it, right? I'm just going to be left out with curl by curl t of psi whole square is equal to iota h bar by 2m curl square psi by curl x square is minus, it is minus iota by h bar v of psi whole square. And we can take something out. That's right. So I can have curl by curl t of psi whole square is equal to iota h bar by 2m. That is minus iota by h bar 2m curl square psi by curl x square, and then minus iota by h bar 2m. So that is just simply psi times psi conjugate. So psi times psi conjugate psi prime prime, and then this will be a minus, that is a psi conjugate. No, is there a psi? Yeah, there is a psi. So this is psi. So this equation, this notation here lied in the psi. This equation lied in the psi conjugate. This equation lied in the psi conjugate. This equation lied in the psi right? Psi as a whole. And then this will be psi conjugate psi minus psi conjugate. I'm not going to go too far. I'm going to wait for some time. I'm not going to go too far. But did you understand what's going on? I'm going to explain it again. What we did was, first of all, I'm not going to go too far. Like I said, you need ordinary differential equations here. Must have ordinary differential equations and partial differential equations. This is a very good reason why you must have ordinary differential equations and partial differential equations. I am going to stop here because not because I cannot do it, but because I'm going to give you guys the time to learn everything from ODEs.